In this video, we are going to talk about limits. So limit is a key concept in calculus and will be used in all sorts of places over the next couple of weeks. So the limit. A limit describes the behavior of a function, f of x, as x gets close to some value. We don't actually care what f of that particular value is, but we care about as f gets close to that value. So let's first do an example and then we'll be a little more formal. So our example is, let's look at the function f of x equals 2x minus 1. And we want to ask ourselves what happens as x gets near 2. So we're trying to figure out the limit as x approaches 2. Now we can approach 2 from either the left or the right. Now if we start from the left below 2, then we see if we put x equals 1.5, we get 2, and 1.9 we get 2.8, and 1.99 we get 2.98 for our function, and 1.999 we get the function's 2.998. Again, we don't care what happens at 2. We know what happens at 2, but we don't care. If we go from the right, as in x is above 2, we put x equals 2.5, we get 4. X equals 2.1, we get 3.2. X equals 2.01, we get 3.02, and so on. And we can see that as x approaches 2, f of x approaches 3. And as I said, you could just plug x equals 2 into your function and you would find out that f of 2 is 3, but that is not always the case, and you can't always plug the number in. Formally, we write the limit as x goes to c, f of x equals L, if f of x is close to the number L whenever x is close to, but not equal to c. Namely, it's either side of c, either to the left or to the right. So let's do some examples. What is the limit as x goes to 0 of the absolute value of x? Well, let's draw a picture for ourselves. From the left, so below, x equals 0, this function looks like this. And from the right, the function looks like this. And both from the left and the right, the absolute value of x approaches 0. Now we look at the limit as x goes to 2 of x minus 2. So let's draw our function again. Well, 1, 2, so the function is a straight line going through these points, and as x approaches 2 from the left, it approaches 0, and as x approaches 2 from the right, it approaches 0, which means this limit is also 0. Finally, let's do the limit as x goes to -1 of x squared plus 1. So this is just a parabola starting at 1. Looks like this, approximately. And when we look at the point -1, I haven't drawn this very well, but from the left, so going down this arm of the parabola, we approach 2. And from the right, going down this arm of the parabola and working our way back up, we also approach 2. So this limit is 2. Now, all of these examples, as I've described them, introduce the concept of a limit from the left and a limit from the right. So we call these one-sided limits. And we write the limit as x goes to c with a minus sign written a little bit above the c. So that means the limit from the left. F of x equals k if f of x is close to k whenever x is close to, but to the left of c. So this limit is, in my previous picture, as we approach from the left. We write the limit as x goes to c with a plus sign, f of x equals j, and call j the limit from the right, or the right-hand limit, if f of x is close to j whenever x is close to, but to the right of c, namely above c. And again, if I go back, that's this limit here as we approach from the right. Now, in order for a limit to exist, The limit from the left and the limit from the right both must exist, and they must be equal. Now, there are plenty of functions for which that's not true. So we want to try to compute the limit as x goes to 2 of f of x. So as x goes to 2 from the left, we can see we're following this function here. This blue line here goes up, and then it goes back down, and the limit from the left is 2. The limit from the right, now we're following this bit of function, and it's working its way up to 5. So the limit as x goes to 2 from the left of f of x is 2. The limit as x goes to 2 from the right, f of x, is 5, which means that the limit does not exist. But the function exists. We can see the function value is just 2. In fact, we have all sorts of limits which exist or do not exist where the function is defined as defined to be something else. Okay, so let's do another example. Let's compute the limit as x goes to 0 of the function f of x again. Well, from the left, we can see it approaches 2. From the right, we can also see it approaches 2, which means that the limit as x goes to 0 of f of x equals 2. Okay, here's another example. What is the limit from the left of our function f of x as x approaches 2? Well, from the left, x is always less than 2, which means we're using this first function. So this is the limit as x goes to 2 from the left of x squared plus 1. And that is simply 5. The limit x goes to 2 from the right, f of x, where x is always bigger than 2, is going to use this function. It's going to be the limit as x goes to 2 from the right of x minus 1, which is just 1, which means this limit does not exist. F of 2, of course, if we go back to our function, we look, well, f of 2 is the function value using the second function, so that's also 1. All right, we have lots of properties of limits, and these properties are reasonably intuitive, so we won't spend too much time on them, but it's just worth knowing. So we're going to have two functions and assume the limits exist. So limit as x goes to c of f of x is some number L. Limit as x goes to c of g of x is some number m. So, some properties. First, the limit as x goes to c of a constant is simply the constant. The limit as x goes to c of the function x is simply c. Limits are additive. The limit as x goes to c of f of x plus g of x is the limit as x goes to c of f of x plus the limit as x goes to c of g of x. We can also subtract our functions. We can multiply a function by a constant. So the limit as x goes to c of k times f of x is equal to k times the limit as x goes to c of f of x. If we multiply two functions together, the limit of the product of two functions is the product of the limits. The limit of the quotient of two functions is the quotient of the limits, assuming the limit in the denominator is not 0. Finally, let's say we take the nth root of a function. So the limit of the nth root of a function is the nth root of the limit, assuming it's defined. And these rules, these properties will let us take all sorts of limits. So for example, the limit as x goes to 2 of x squared minus 3x is, I'll write it out, x goes to 2, x squared minus the limit x goes to 2 of 3x equals the limit x goes to 2 of x squared minus 3 times the limit x goes to 2 of x. The limit as x goes to 2 of x is just 2, so that's 2 squared minus 3 times 2, which is negative 2. The limit as x goes to 4 of 2x divided by 3x plus 1 Again, we can break this into parts. Limit as x goes to 4 of 2x divided by the limit x goes to 4 of 3x plus 1, which is 2 times the limit x goes to 4 of x divided by 3 times the limit x goes to 4 of x plus the limit x goes to 4 of 1. This is just a 4, right? Limit as x goes to 4 of x is 4, so 2 times 4 is 8, divided by 3 times 4 is 12, plus, this is a constant, 1/13. So 8/13. Limit as x goes to 2 of the natural log of x squared is, as roughly expected, the natural log of 4. So we can do all sorts of things. I've cheated a little bit because I haven't given you that rule on the limits, but this makes sense.